One of the things that attracts many scientists to their profession is the excitement of discovering something new. You can imagine the excitement in the scientific community when the Large Hadron Collider recently found something entirely new. The discovered object is so elusive that some scientists have described it as a ghost. What has the collider just discovered? Why did it remain hidden for so long? In this video about the mysteries of the universe, we bring you how scientists just announced that the Large Hadron Collider has found something for the first time ever. Many people go about their day without knowing about the Large Hadron Collider. However, the discoveries made by the massive apparatus affect the life of everybody in the universe. Take as an example the latest particle that scientists just spotted for the first time with the help of the infrastructure. The Large Hadron Collider, or LHC, is the biggest and most powerful particle accelerator ever built. Covering an underground circular tunnel that is nearly 17 miles in circumference and costing billions of dollars, it is located at the European Particle Physics Laboratory CERN in Switzerland. But what exactly is a particle accelerator and why is it needed? It is a device that boosts subatomic particles to enormous energy in a controlled environment. This allows scientists to study the interaction that comes after. So basically, LHC helps scientists to test theoretical predictions and see if they have any loopholes. The LHC can be used to reproduce scenarios, including the conditions within a billionth of a second of the Big Bang. These include conditions that have never existed naturally since a few microseconds after the Big Bang. This facility is so key to modern scientific research that if there is any headline about subatomic particles, the LHC will most likely be involved. So when headlines across the world said physicists had detected ghost particles for the first time inside an atom smasher, it was obvious what equipment they used. Neutrinos are notoriously elusive, which is why news of the discovery made waves. The particle in question, the neutrino, opens up a completely new window for scientists carrying out subatomic research. They came a step closer to understanding the roles neutrinos play in the universe. While neutrinos are not easy to spot or catch, they are numerous in the universe. For instance, while you watch this video, about 100 billion neutrinos pass through each square centimeter of your body. But of course, you won't feel their entry or exit. These tiny particles are everywhere. They originate in nuclear fires produced by stars, supernova explosions, cosmic rays, radioactive decay, and more. Neutrinos manage to go undetected because they have zero electrical charges and nearly zero mass as well. They are 6 million times lighter than an electron. They almost don't react with any form of matter, but move at almost the speed of light. It is this elusive nature that makes people liken them to ghosts. But of course, if you try hard enough, you can catch neutrinos, but you must try very hard. A few experiments before now have discovered neutrinos. These include Japan's Super Kamiokande detector, Fermilab's Mini Boon, and the Antarctic Ice Cube detector. They all used a method known as the Cherenkov radiation, which is actually an indirect way to detect neutrinos. This is the gist of using the Cherenkov method to detect neutrinos. When a plane travels faster than the speed of sound, it creates a sonic boom. Similarly, when a particle travels at the speed of light through a light-slowing medium like water, it produces a faint blue glow that follows it. Scientists look for this glow when a neutrino strikes an atomic nucleus directly. However, this method only detects the signatures of neutrinos as they pass through the Earth coming from the Sun. It doesn't, for example, give any insight into the type of high-energy neutron that is produced when particles smash into each other, as can be observed in a particle accelerator like the LHC. On its own, the LHC cannot detect neutrinos. This is partly because the collider employs magnets to direct particles around a circular collision path with the detectors dotted around these curves. These magnetic traffic signs don't impact chargeless particles like neutrinos. As a result, they shoot off the edge of the detector path. To investigate this, scientists under the Phaser collaboration created a new neutrino detection mechanism, which they named the Phaser NU. This Phaser NU is made from dense metal plates of lead and tungsten. These plates sandwich some layers that can detect light, known as an emulsion. The first step is to make the neutrinos crash into the atomic nuclei on the metal plates, which produces particle byproducts. The next step is a familiar one for older photographers. The emulsion byproducts react with the neutrino byproducts, which imprints the outlines of the particles as they pass through the emulsion layers. When they developed the emulsion and analyzed the particle trails left behind, the researchers realized that some of the marks were produced by neutrinos. In fact, they were able to determine which of the 3 particle flavors of neutrino they had detected. The flavors are tau, muon, and electron. This result assured them that they had picked the right spot inside the gigantic LHC ring to detect neutrinos, and also that their new detector was actually able to see them. Phaser NU is better than the experiments before it in several ways. For instance, the Super Kamiokande requires 50,000 tons of water. In contrast, Phaser NU weighed only 29 kilograms. It was also made from leftover parts at CERN. Remember we said that there are 3 flavors of a neutrino. Tau neutrinos are the rarest and most challenging to detect. In fact, before the advent of Phaser NU, tau neutrinos had only been observed 10 times, the first time about 20 years ago. Phaser NU is powerful enough to detect different flavors of neutrinos, but it can also distinguish between neutrinos and antineutrinos. And here is where it gets interesting. Antineutrinos are just neutrinos with the opposite charge. You may recollect we said neutrinos do not possess a charge, and this information may appear contradictory. However, both neutrinos and antineutrinos are electromagnetically chargeless. The opposite charge actually stands for a neutron's lepton number, or a kind of quantum number used to describe the properties of subatomic particles. There are loads of questions that scientists don't have answers to just yet about neutrinos. For example, they do not know for certain the difference between a neutrino and an antineutrino. But Phaser NU will help them to learn more about neutrinos. The team behind Phaser NU said they would spend 2022 chasing and capturing 10,000 or more neutrinos. The answers to some of these questions will help in answering questions like where matter comes from and why so much of it is dark. Now, when scientists are investigating supernovas, you expect them to be observing the sky overhead, right? You'll be shocked to know where astronomers have been looking in recent times. The quest to know more about supernovas is making them examine trees for clues. They're examining tree rings for evidence of past supernovas. But what is the connection between trees on the Earth and supernovas occurring at billions of miles away from us and billions of years ago? When a star dies, it often does so in a spectacular fashion. There is an explosion followed by the star's outer materials scattered in the universe. The result is that space gets bombarded with high-energy gamma radiation for several years. What scientists are trying to do is ferret out evidence of the death of stars from trees. Supernovas are not common, even though there are uncountable stars in the universe. While there is no way to determine how often a star explodes, even in our own Milky Way galaxy, some observations claim we could have between 1 to 3 supernovas in a century. But the most recent one in history took place more than 400 years ago. Robert Breckenridge is a geoscientist at the University of Colorado Boulder. He and his colleagues found what could be the fingerprints of nearby ancient supernovae in tree rings dating back to 40,000 years ago. The team claimed that in the last 15,000 years, there have been 4 supernovae close enough to Earth to leave their signature in the trees. So how does this work? The clue is the abundance of a radioactive isotope of carbon called carbon-14, or radiocarbon. Radiocarbon only occurs on Earth in trace amounts compared to the other naturally occurring carbon isotopes. Radiocarbon is formed in the upper atmosphere as it is bombarded by cosmic rays from space. When cosmic rays enter the atmosphere, they interact with the local nitrogen atoms to kick off a nuclear reaction that produces radiocarbon. And since cosmic rays are constantly streaming through space, Earth receives a more or less steady supply of radiocarbon. And if you know where to look, you will find radiocarbon. For example, some of this can be found naturally in tree rings, and every now and again, a large radiocarbon spike turns up in the tree rings, fading over several years. Since a rather significant known source of cosmic rays is solar activity, these spikes are usually interpreted as evidence of solar flares and storms. Every year, trees that are not near the equator grow during the temperate months but go dormant come winter. This pattern of growth and non-growth forms a ring inside the wood making up the tree. You can observe the ring when the tree is felled. The rings near the surface of the tree are the newest, and they age as the ring approaches the center. Counting the rings can reveal the age of a tree. A practical application is archaeologists using the pattern of tree rings in the wood found in ancient structures to determine when they were built. Breckenridge applied this knowledge to determine what might happen to tree rings when supernovae occur. He reasoned that a nearby supernova would give off vast amounts of what is called gamma radiation. Radiocarbon absorbed by a tree will make the rings more radioactive than one another. To test how valid the supernova hypothesis is, Breckenridge and his colleagues checked the record books. They compiled a list of known supernovae over the last 40,000 years. They were able to trace the supernova through the nebulous supernova remnants they left behind. Then they compared this list to the record of radiocarbon spikes in tree rings from the same period. What did they discover? Well, all 8 supernovas closest to the Earth seem to have matched periods of spikes in radiocarbon. For example, the Vela supernova, which exploded around 12,300 years ago at a distance of 800 light-years from Earth, corresponded with a 3% rise in radiocarbon. The G114.3 plus 00.3 supernova, which exploded around 7,700 years ago at a distance of around 2,300 light-years, corresponded with a 2% rise. There is also the Vela Junior, which was estimated to have occurred about 2,800 years ago. During that period, the Earth recorded a 1.4% radiocarbon spike. They also found supernova HB9, which took place some 5,400 years ago at a distance of between 1,000 and 4,000 light-years. This one corresponded with a 0.8% jump in radiocarbon levels. Scientists are now trying to validate Breckenridge's discovery. They are hoping that the tree rings method will help them nail the timing of many supernovas that have been difficult to date. They will also gain more understanding of how stars explode. One of the most powerful hints we have in physics that new discoveries are on the way is the discovery of a mechanism that could explain why the universe has the properties we observe it to have. However, none of this proves that magnetic monopoles exist. Rather, it merely suggests that they might. But scientists have not given up on looking for monopoles, and it's important they don't. Why? Whenever scientists consider a theoretical idea, one of the things they look for are pathologies. That is, reasons that whatever scenario they're investigating would break the universe in some way or another. When 't-Hooft Polyakov monopoles were first proposed, one such pathology was discovered. Magnetic monopoles would do something known as overclose the universe. In the early universe, things are hot and energetic enough that any particle-antiparticle pair you can create with enough energy will get created. When symmetry is broken, you can either give a previously massless particle a non-zero rest mass, or spontaneously rip a large number of particles or particle-antiparticle pairs out of the vacuum. The first case is what happens when the Higgs symmetry breaks. The second case is when the Pache-Quinn symmetry breaks, allowing axions to escape the quantum vacuum. In either case, this could have disastrous consequences. The universe normally expands and cools, with the overall energy density closely related to the rate of expansion at any given point in time. If you either give a large number of previously massless particles a non-zero mass, or add a large number of massive particles to the universe, suddenly and spontaneously, the energy density increases rapidly. With more energy present, the expansion rate and energy density are suddenly out of balance. There is simply too much stuff in the universe. This causes the expansion rate to not only fall, but in the case of monopoly production, to fall all the way to zero before contracting. In short order, the universe collapses, resulting in the Big Crunch. This is known as overclosing the universe, and it can't accurately describe our reality. We are still here and nothing has recollapsed. This conundrum is also known as the monopole problem, and it is one of the 3 primary drivers of cosmic inflation. In the same way that inflation stretches the universe from whatever its geometry was previously to a state indistinguishable from flat, solving the flatness problem and imparting the same properties everywhere to all locations within our observable universe, solving the horizon problem, it can solve the monopole problem as well, as long as the universe never heats back up to above the grand unification scale after inflation ends. How have scientists been looking for magnetic monopoles? In 1981, experimental physicist Blas Cabrera built a cryogenic experiment involving a coil of wire explicitly designed to search for magnetic monopoles. He reasoned that by constructing a coil with 8 loops, if a magnetic monopole ever passed through the coil, he would see a specific signal due to the electric induction that would occur. Passing one end of a permanent magnet into or out of a coil of wire induces a current, but passing a magnetic monopole through that coil of wire should induce an electric current that corresponds to exactly 8 times the theoretical value of the magnetic monopole's charge due to the 8 loops in his experimental setup. However, if a dipole passed through, there would be a signal of +8 followed by a signal of -8, allowing the two scenarios to be distinguished. Now, on February 14, 1982, no one was in the office monitoring the experiment. Cabrera returned the next day and was astounded by what he saw. The experiment produced a single signal that was nearly identical to what a magnetic monopole should produce. This sparked a lot of interest in the project. Did this imply that inflation was incorrect and that we actually lived in a universe with magnetic monopoles? Did this imply that inflation was correct and that the one monopole that should have persisted in our universe happened to pass through Cabrera's detector? Or did it imply that this was the pinnacle of experimental blunders, a glitch, a prank, or something else that we couldn't explain but was clearly erroneous? A slew of copycat experiments followed, many of which were larger, ran for longer periods of time, and had more loops in their coils, but no one else ever saw anything resembling a magnetic monopole. But the search for monopoles has been heartily taken up by CERN and its scientists. The Large Hadron Collider, or LHC, is the world's largest and most powerful particle accelerator located at CERN. The LHC is comprised of a 17-mile or 27-kilometer ring of superconducting magnets and a series of accelerators that fire high-energy particles through the apparatus like a bullet through a gun. The collider, which is located 328 feet or 100 meters below ground, blasts a beam of protons in one direction while another beam travels in the opposite direction. At maximum speed, the particles collide at 99.9999991% the speed of light. Every time protons collide, a complex spray of other particles is produced. Many of these particles have a lifetime of less than a second, but they leave a trail of subatomic breadcrumbs that scientists can follow. Scientists rely on 2 highly complex detectors to follow that trail, which allows them to see the fundamental building blocks of our universe. Atlas is one of these detectors. The machine, which is about 148 feet or 45 meters long and 82 feet 25 meters tall, assisted in the discovery of the Higgs boson. Atlas is half the size of Notre Dame, the cathedral, not the university, and twice the weight of the Eiffel Tower, the one in Paris, not Las Vegas. CERN scientists use Atlas and other detectors, ALICE, CMS, LHCb, LHCf, to investigate topics that are only discussed in science fiction, such as whether other dimensions exist, what type of unifying force exists in the universe, and whether there is evidence of dark matter. Atlas and CMS were the only detectors dedicated to solving the Higgs boson mystery. All experiments at the LHC are unique and are run by a global collaborative team of scientists. It's one thing to smash particles together at nearly the speed of light. It's quite another to interpret the data generated by those collisions. Particles collide nearly 600 million times per second in the LHC. The information emitted by those crashes can tell us a lot about the inner workings of the atom and the forces that hold it together, but we can't record everything from the detectors. Atlas, for example, could fill 100,000 CDs with data every second if CERN did. Instead, Atlas, like the other detectors, can only record a smidgen of data, equivalent to about 27 CDs per minute. During reconstruction, scientists tested their theories about how particles behave. They contrast computer-simulated collisions with real-world collisions. A difference between the two could indicate new science, something previously unknown. Every day, the data center processes 1 petabyte of data. To hold all of the information in a petabyte, 223,000 DVDs would be required. To make matters worse, scientists sift through 30 petabytes of data each year, making new science extremely difficult to find. And now, a new class of experiments at the Large Hadron Collider at CERN, first envisaged by imperial physicists, have created conditions more likely to produce monopoles. Despite the fact that no monopoles have yet been discovered, the new experiments have allowed researchers to fine-tune the likely properties of monopoles, directing the course of future experiments. While physicists' ability to draw conclusions from previous experiments at the LHC and elsewhere has been limited, these new experiments, which use a different production mechanism, allow us to definitively rule out the existence of certain types of monopoles and have given us a much better idea of where the search for monopoles can go next. In 2018, the LHC smashed together a different kind of particle, heavy ions in the form of lead nuclei. Because these particles contain hundreds of protons and neutrons, they can only collide at lower energies than single proton collisions. However, if these lead nuclei clip or pass very close to each other, the interaction can produce something spectacular. The universe's strongest magnetic fields are 1,000,000 times stronger than those found in neutron stars. These exist for a very short time, but they provide a different mechanism for producing magnetic monopoles. The theory is based on a mechanism for producing electrons and their antimatter equivalent, positrons, the electrical equivalent of monopoles. According to the Schwinger mechanism, which was proposed in the 1930s, a strong electrical field will interact with quantum fluctuations in a vacuum, producing electrons and positrons. A strong magnetic field should also produce north and south monopoles. While no evidence of monopoles was detected, the organization made a very strange announcement. A crack in the Earth's magnetic field appeared and remained open for nearly 14 hours. A rare phenomenon known as a co-rotating interaction region (CIR) from the Sun caused the crack in the magnetic field. CIRs are large-scale plasma structures formed when fast and slow-moving streams of solar wind interact in the heliosphere's low and mid-latitude regions, which include the solar magnetic field and the solar winds. CIRs, like coronal mass ejections, CMEs, are flung out from the Sun towards Earth and can contain shock waves and compressed magnetic fields, resulting in stormy space weather, which usually manifests as beautiful aurorae. Coronal mass ejections, like solar flares, are caused by the twisting and realignment of the Sun's magnetic field, a process known as magnetic reconnection. When magnetic field lines tangle, they produce strong localized magnetic fields that can break through the Sun's surface at active regions, resulting in CMEs. CMEs typically occur near sunspot groups and are frequently accompanied by a solar flare, though the two do not always occur simultaneously. CMEs, like solar flares, are most common during solar maximum, a period in the Sun's 11-year cycle of activity when the star is at its most active. CMEs swell in size as they travel away from the Sun after they're released. Larger CMEs can fill nearly a quarter of space between Earth and the Sun by the time they reach our planet. If a CME is large enough and travels faster than the solar wind, it generates a shock wave in which accelerated charged particles travel ahead of the CME, disrupting space weather conditions and intensifying geomagnetic storms. And while CMEs produce beautiful auroras, they can be destructive. Large CMEs can cause technological malfunctions, which are especially troublesome in today's world. For example, the Carrington event in 1859 disrupted the global telegraph system. There were even reports of operators getting electric shocks and sparks from telegraph machines igniting papers. And according to NASA, a CME accompanied a solar flare that hit Earth in 1989, causing an electrical blackout that lasted 12 hours in the entire province of Quebec, Canada. The event caused at least $10 million in damage to Quebec's utility company, Hydro-Quebec. But how exactly do CMEs cause all of this havoc? CMEs can cause electrical current surges that overload power grids, resulting in widespread blackouts. And that is in addition to jostling the Earth's magnetic field, impairing radio transmissions and increasing radio static in the ionosphere. GPS systems are especially vulnerable to ionosphere disturbances, and GPS coordinates have been known to stray by tens of feet during a CME event. GPS uses radio signals to relay information between a satellite and a ground receiver, which causes the disruption. The radio signal passes through the ionosphere layer, which contains charged plasma that bends the path of the GPS signal in the same way that lenses bend light. Normally, GPS systems can compensate for this bending of the radio signal, preserving GPS accuracy. During a CME event, however, the ionosphere can be so severely disrupted that GPS models are unable to keep track of such changes, and receivers are unable to calculate an accurate position. Also, Earth-orbiting satellites are vulnerable to CMEs, particularly those in high geosynchronous orbits, which is where the majority of communication satellites are located. Satellites can be struck by a high current discharged into the satellite or damaged when high-energy particles penetrate the satellite when a CME causes a geomagnetic storm. As a result, vulnerable satellites can be put into safe mode to prevent electronic damage. SpaceX saw firsthand the devastation that space weather can cause last year when a geomagnetic storm destroyed up to 40 Starlink satellites, worth more than $50 million in February. The magnetic field protects us against solar storms caused by the sun. It was previously thought that they opened and closed quickly, but we now know that they stay open for hours. Scientists discovered that our magnetic shield is drafty, like a house with a window left open during a storm. The house deflects the majority of the storm, but the couch inside the house gets destroyed. Similarly, our magnetic shield absorbs the brunt of space storms, but some energy escapes, causing problems with satellites, radio communication, and power systems. And the sun is nearing its most active period in the solar cycle around July 2025 and is already unusually active for this early in the cycle. What this means is that your chances of seeing the aurora are now excellent, and they will continue to improve over the next 3 years. Now, there are valid reasons to be concerned about the effect of something happening to the Earth's magnetic field. Perhaps the most terrifying effect of losing the Earth's magnetic field might be losing the air we breathe, and the culprit would be the solar wind once again. The sun's natural wind is so powerful that it can easily rip gases from a planet's atmosphere until there is no gas left. In fact, that is most likely what happened to Mars. Mars was most likely once similar to Earth, with oceans of water and a dense atmosphere. But unlike our planet, its magnetic field vanished billions of years ago. Its atmosphere was completely unprotected, and it was ripped away into space. When its atmospheric pressure fell low enough, its water began to evaporate and was carried away by the solar wind too. It's entirely possible that without our geomagnetic field, our atmosphere, oceans, and life on Earth would perish in the same way. But before the atmosphere is stripped away, animal life would be affected on our planet. Humans aren't the only animals that use the Earth's magnetic field to guide them. Many birds, sea turtles, lobsters, honeybees, salmon, and even fruit flies have biological compasses known as magnetoreceptors built into their bodies. During the winter, birds use this ability to migrate to warmer climates, while sea turtles use it to navigate the open ocean and find beaches to lay their eggs. Scientists believe that most female sea turtles return to the same beaches year after year, thanks in part to their natural compasses. Many animals that rely on compass navigation could be in serious danger if the Earth's magnetic field vanishes. Sea turtles can become disoriented at sea. Migratory birds may fly in the wrong direction, endangering their lives. Honeybees may become disoriented while searching for their hives, affecting flower and plant pollination. These and many other organisms may face extinction as their navigational abilities deteriorate. Let's hear what you think of the Earth's magnetic field in the comments section below.